From Cape Canaveral in Florida, this is Falcon Launch Control at T-minus 1 hour, 20 minutes, 8 seconds, and counting. The countdown is on schedule for the launch of the SpaceX CRS-5 Falcon 9 with the Dragon capsule bound for rendezvous with the International Space Station. Liftoff continues to be targeted for a liftoff at 6:20 a.m. this morning. The Dragon capsule was powered on atop the rocket yesterday morning at T-minus 28 hours, or at about 2:20 a.m. The pre-launch activities have been underway at Space Launch Complex 40 since about 8:20 last night, when the Falcon 9 rocket was powered on after completing the late cargo storage. The Falcon 9 was then raised to vertical at approximately 9:20 p.m., and shortly thereafter there was a vehicle verification with the tracking and data relay satellite system. The launch pad was cleared of personnel at 1:20 a.m., and the call to stations for the SpaceX launch team in preparation for fueling occurred at about 2 a.m. This is the terminal phase of the countdown, which is 4 hours and 10 minutes in duration, and there are no built-in holds. Loading of the RP-1 fuel, a highly refined rocket-grade kerosene, began at 3:20 a.m., and was followed by loading of liquid oxygen, which began at 3:45 a.m. Fueling of the Falcon 9 was completed at 4:50 this morning. The S-band telemetry and video transmitters on the rocket have been checked out, and the flight termination system checks with the Eastern Range have been completed. Upcoming at T-minus 1 hour will be a weather briefing. The launch computer's automated terminal countdown sequence for the Falcon 9 and Dragon capsule is initiated at T-minus 10 minutes. At T-minus 2 minutes, the SpaceX launch director gives a go for launch, and concurrence is received by the range control officer from the Air Force Eastern Range. At T-minus 60 seconds, the flight computer will begin the final pre-launch checks. And at T-minus 40 seconds, the Falcon 9 propellant tanks will be pressurized for flight. Finally, at T-minus 3 seconds, the main engine controller aboard the vehicle commands engine ignition sequence to start for the liftoff. All of our countdown activities continue to proceed. Our weather forecast looks excellent. It's gradually been getting better over the course of the night, and we'll be getting a forecast from our launch weather officer, Mike McAleenan, at T-minus 60 minutes, or at about 5:20 this morning. At T-minus 1 hour, 17 minutes, 17 seconds and counting, this is Falcon Launch Control. This is Falcon Launch Control at T-minus 1 hour, 13 minutes, 40 seconds, and counting. Joining us here in the Mission Director Center now is Stan Scott. He is the CATS Instrument Manager. And CATS, first of all, Stan, tell us what CATS stands for.
All right. Hey, George. The CATS instrument stands for Cloud Aerosol Transport System, and that's Earth Remote Sensing instrument that was designed and built at the Goddard Space Flight Center in Greenbelt, Maryland.
Why is the CATS measurement important to Earth science?
Well, let me tell you a little bit more about what CATS is.
Okay,
before we get to that point. You know, CATS is what's known as a LiDAR instrument.
And that stands for?
That stands for? Actually, it's one of those acronyms that people aren't really sure exactly what it stands for.
Okay, but it's a laser instrument, right?
Yes. It's very similar to the way that sonar works or radar works, but in place of using sound or radio waves, CATS, as a LiDAR instrument, uses short pulses of low-energy laser light. And that light travels through the atmosphere, and as it's traveling through the atmosphere, it encounters clouds, particles, aerosols, pollutants, and as that pulse of light hits those particles, some of it's scattered back. And the light that's scattered back is collected by our telescope in the instrument and sent to our sensitive detectors. And those detectors count the time between when the laser pulse exits the instrument and when the light returns. And by doing that, we're able to build up a profile of the atmosphere. And the scientists are able to use that that profile to study the atmosphere.
All right. So that then brings me to the question that I was asking: is why is the measurement important to Earth science?
Well, George, the amount of particles and pollutants in the Earth's atmosphere have a direct effect on human health. If the scientists can study where these pollutants and aerosols are at, then they can better understand the effects that they're going to have on human health and where to actually, hey, this is a code red day, this is a code orange day. They can kind of tell that beforehand, predict it a little bit earlier. Also, the study of cloud heights allows scientists to better predict global temperature. Clouds are the primary regulator of global temperature. The type and height of the clouds determines how much sunlight is allowed through to the Earth's surface and how much of the sunlight is allowed to be radiated back out away from the Earth. So, if you have more clouds, depending on the type of clouds, it might actually end up being warmer or colder.
All right. Well, how is CATS much more than a technology experiment?
Well, let me get back to the third thing, is that the data that's gathered by CATS will be transmitted back down to our ground station in near real time. And this data will be used, processed very quickly at our ground station, and then that goes out to the models within about 2 hours to go into the global models. Now, as far as how is it much more than a technology experiment, CATS is the first NASA payload to use the Japanese experiment module exposed facility, also known as the GEM-EF. CATS was the first instrument by NASA to use this facility, and it's used as a forcing function to define and refine the ISS procedures for handling instruments like ours. CATS was also the first instrument from the U.S. that's going up on a U.S. payload, the first GEM-EF payload that's going up on a U.S. transport. So the hardware that was needed to hold a GEM-EF experiment had to be developed, and SpaceX was able to develop that hardware so we can fly up on the Dragon today.
So that means it's being mounted on the GEM? Is that where it will be?
Well, it will eventually go to the GEM. That hardware's already there, but the hardware, in order to hold it to the rocket, had to be developed.
Okay.
And then third, and most importantly, CATS has been an experiment in managing a true build-to-cost, build-to-schedule payload. It was an experiment in streamlining the processes and procedures to maximize the science return while minimizing cost. We built this instrument in about 2 years, and we spent, about $15 million. On the screen, you can see, what the instrument actually looked like.
Now, you had students involved with the mission. How do the students contribute to this CATS instrument?
Well, George, we had three very excellent students who were able to come in between when they completed high school and before they started college. Um, One of those students was a kid who worked for me, or not worked for me. I mentored him in robotics, and he was able to do a lot of the optomechanical integration and testing that was necessary for the instrument. He also did a lot of the telescope acceptance testing for us, and he was very nervous about that at first. But once I mentored him and showed him exactly what he can do and what he shouldn't do, he was great. We had another kid who came in. He did a lot of the mechanical design. He designed some of the parts for the instrument. He also did the mechanical design for the ground support equipment that we use on the instrument for handling the instrument. And we had a third student who came in, and he was another one of the students that I had mentored in our robotics program. And he was able to design the software that we needed for opening and closing the hatch that you saw a little bit earlier. The door, the telescope aperture covers, and the what we have is an alignment mechanism in there that moves some motors around, and he was able to design all the software for that. So he did an awesome job for us.
So can you say there's something that you learned from the students that were involved in the project?
Absolutely. We learned that if you trust the students, if you empower them, if you mentor them properly, you can expect great things from them.
So this initiative took about how long from the time that you began until we reached today?
Oh, it's been 3 years now.
3 years.
3
okay.
years.
All right. Well, Stan, thank you very much. I'm sure you're going to be watching with a lot of interest the mission aspect.
Oh, absolutely. We're very excited about this.
So, thank you so much. Stan Scott, the CATS instrument manager from NASA's Goddard Space Flight Center. We're now at T-minus 1 hour, 6 minutes, 38 seconds and counting. This is Falcon Launch Control. This is Falcon Launch Control, T-minus 1 hour, 5 minutes, 4 seconds, and counting. After liftoff from Complex 40 at Cape Canaveral this morning, Dragon will begin its journey to the International Space Station. Just under 10 minutes after launch, the capsule will reach its preliminary orbit, deploy its solar arrays, and begin a carefully choreographed series of engine firings to rendezvous with the International Space Station. At the time of launch this morning, the space station will be located at an altitude of 261 statute miles over southeast Iraq. The initial planned orbit is 227.1 by 123.8 statute miles at an inclination of 51.6 degrees. The initial apogee, or high point of the orbit after launch, is below the ISS by about 35 miles. And on its 2-day chase, as it pursues the space station, Dragon will be at an average altitude of 175.4 statute miles. With the launch today, the rendezvous and grapple with the International Space Station will occur on Thursday, January 8th at 6 a.m. Eastern Time. And at that point, the ISS will be located 262 miles above the northern Atlantic west of Ireland. We're standing by here for our weather briefing from our Air Force Launch Weather Officer, Mike McAleenan, who will be briefing the launch team on the forecast for today, which occurs at exactly T-minus 60 minutes in the countdown. So we are about 3 minutes and 20 seconds away from the weather briefing this morning. At T-minus 1 hour, 3 minutes, 10 seconds and counting, this is Falcon Launch Control. At T-minus 1 hour, 17 seconds and counting, this is Falcon Launch Control. And we're standing by now in about a quarter of a minute for our weather briefing by Launch Weather Officer Mike McAleenan from the 45th Weather Squadron.
This is the LWO with the L-minus 1 hour range weather briefing. On your weather video, you can see the water vapor is still showing a nice swath of moisture associated with the jet stream in the upper levels across the northern half of the Florida Peninsula. Zooming in a little closer, you can see that cloud is beginning to thicken a bit. We are seeing some enhancements on the infrared image just to our north and west. And we are starting to now see that on radar as well, just a few pixels at the 0 dBz level between 40 and 70 nautical miles to our west and northwest. The height of those clouds keep it in the ice crystal level and not a concern for launch. Looking at the launch pad, you can see winds have trailed off nicely and are sitting around 7 or 8 knots at 162 feet at the launch pad. The direction has transitioned from a northerly component to a north-northeasterly component, now sitting around 70 degrees or so, and expected to remain in that category for the next hour to the launch window. Temperature with that wind shift has also increased a bit with the onshore flow and is now sitting at around 69 degrees. On the upper levels, we are seeing some good agreement with the various balloons that have been launched and the test of the 50 megahertz Doppler profiler. And we are seeing that maximum wind, as forecast, around 48 to 49,000 feet at around 85 knots out of the west. Looking at the solar weather, see proton flux is remaining in the normal background levels, well below the constraint. So looking at no issues for launch for that. Needless to say, we are go on all launch commit criteria and for the range and for SpaceX. Forecast remains favorable for the remainder of the launch countdown, and for T0, there's few clouds in the sky at 3,000 and 12,000, and that upper level cirrus of no concern at 25,000. We're only at 10% chance of a violation, with the main concern being the thick cloud rule. If we were to delay to Friday, skies will be even a bit more favorable, which is scattered conditions. Winds a bit more problematic with a 2 or 2.5 days of onshore flow with a potential of a stray rain shower in the early morning hours, so a 20% chance of violating a flight through precipitation. Other than that, looking real good for the remainder of the window, and that's all I have, pending any questions.
This is Falcon Launch Control, T-minus 53 minutes, 49 seconds, and counting. The Dragon capsule on this flight tonight will transport a total of 5,108 pounds of cargo to the International Space Station, including food, water, and clothing for the astronauts, and science experiments from the U.S., Japan, and the European Space Agency. Dragon is actually capable of carrying up to 7,300 pounds of supplies to the space station. After 4 weeks in space, the crew will download into the Dragon approximately 3,600 pounds of cargo, including completed science experiments and expended consumables to be brought back to Earth. Once in orbit, Dragon will have a link with a network of ground tracking stations around the world, as well as with NASA's tracking and data relay satellite system. For its return, approximately 4 hours after Dragon leaves the station, Dragon will conduct its deorbit burn, which lasts about 7 minutes, and then it will take about 30 minutes for Dragon to re-enter the Earth's atmosphere and splash down in the Pacific Ocean off the coast of Baja California. Right now here in the Mission Director Center, we're being joined by Dr. Daniel Woodard. He is an aerospace medicine research physician at KSC, and he's going to be talking to us some about the biomedical research on the International Space Station. And Dr. Woodard, first of all, can you tell us a little bit about how this flight accomplishes medical research on the ISS?
Well, our research has, for the past 10 years, has as one of its focuses, we have looked at the biochemistry behind Alzheimer's disease, the molecular processes that first begin the degeneration that occurs in the human brain, how molecules really interact. And the flight on the space station will give us an opportunity to observe these processes without the influence of gravity. This is important because the key step is one in which protein molecules apparently stick together, much like marshmallows, to form long chains, thread-like structures that accumulate in and around the nerve cells in the brain and cannot be removed by the body's normal processes. It's sort of like sludge forming in your crankcase if you don't change your oil. This is possible to study on the ground, but it's difficult because as these structures get larger, they no longer will remain suspended in fluid and will simply precipitate to the bottom of a test tube or container. In space, they will be able to float in the fluid much as they would in living tissue, and we believe that these proteins will assemble into larger and more regular structures. We can then examine what these structures are using atomic force microscopy and other processes. One of them is called X-ray diffraction. It is sometimes used to look at the structure of molecules, proteins in crystals that have been formed in space in the past. And we hope these same techniques may be applicable in our study of Alzheimer's disease.
Now, what's the design of the flight hardware?
The flight hardware is extremely compact. It fits within a cube, 10 centimeters on each side, or about 4 inches. And within that small cube, our experiment designers have been able to fit 9 incubation chambers, each one of them sealed with a small mechanism that can mix protein and fluid buffer in which it is dissolved. Heater coils to raise the temperature to the appropriate level, electronics that controls the temperature, and so on. So an entire experiment can be prepackaged in this small box, which would easily fit in a briefcase.
What specific medical research is going to be done aboard the ISS going up on this mission? I think there's a couple of well-known diseases to which people could relate.
Yes, our experiment relates to both Alzheimer's and Parkinson's disease. I want to stress that this isn't an experiment that produces a cure or a sudden breakthrough. I don't really believe that's the way science works. real progress always involves many many experiments, each of which advance our knowledge a little bit. And the main advance we hope to get out of this experiment is simply to understand whether proteins can undergo this aggregation process without the force of gravity, and how gravity influences that aggregation.
Well, how much involvement do the astronauts need to have with it?
Well, astronaut time is very critical on the space station. Most of the astronaut time is taken up with keeping the space station functioning, moving supplies and things of that sort, maintaining their own health. And so I think it's important, if we're going to have high productivity for science on the space station, that experiments be highly automated. In our case, the experiment just has to be placed in the appropriate area. The nanoracks, whole nanoracks assembly is stowed by the astronauts, and power has to be provided, and that's really all that they have to do. The entire experiment is automated.
Well, speaking of the power, how much power does it take to run it?
This experiment actually runs off an ordinary USB cable, just like you might use to power your mouse or plug in your cell phone. The amount of power that it requires is very small, and consequently the space station is capable of supporting a large number of different experiments from different investigators.
Well, Dr. Woodard, thank you very much, and I'm sure you'll be looking forward to the outcome of this and maybe more follow-on of this kind of thing in the future. Dr. Daniel Woodard, Aerospace Medicine Research Physician at the Kennedy Space Center.
Thank you very much, George, for the opportunity.
We're now at T-minus 47 minutes, 4 seconds, and counting. This is Falcon Launch Control. This is Falcon Launch Control, T-minus 42 minutes, 18 seconds and counting. We're on schedule for a liftoff at 6:20 a.m. this morning. We're looking at a live shot now of the Falcon 9 rocket with the Dragon capsule at SpaceX Space Launch Complex 40 on Cape Canaveral Air Force Station. The launch team, the SpaceX launch team, is at the SpaceX Falcon 9 Launch Control Center, which is on Cape Canaveral Air Force Station near Gate 1, and this is where the team actually is going through the process of commanding the Falcon 9 and the Dragon capsule this morning, and we'll be activating all of the systems to begin the terminal launch countdown sequence, which will be picking up here in about another 20 minutes. We go out to California to Hawthorne. This is the mission control room at Hawthorne, the SpaceX facility that will be monitoring all of the data as it comes back from the Falcon 9 rocket as it does its ascent into space, as well as from the Dragon capsule during the flight and after separation from the Falcon 9. It's also a SpaceX team in Hawthorne at their Mission Control Center. And this is the flight control room in Houston at the Johnson Space Center, the ISS Mission Control Center, where all of the activity is being monitored for the launch and flight of Dragon today, and then most importantly, the rendezvous with the International Space Station coming up day after tomorrow. The Falcon 9 rocket with the Dragon spacecraft is 157 feet in length, 12 feet in diameter, and weighs 735,000 pounds. There are 9 SpaceX Merlin engines powering the Falcon 9. The rocket is held down on the pad and not released for flight until all propulsion and launch vehicle systems are confirmed to be up and running properly. And then after the liftoff, the first stage will burn for 3 minutes before separating from the rest of the rocket. A single Merlin engine on the second stage will burn for 5 3/4 minutes before the Dragon separates from the Falcon 9 minutes 35 seconds after launch. After the liftoff, mission control for the Falcon 9 will switch to the Hawthorne SpaceX facility. Dragon will have a link with a series of ground tracking stations around the world and will also be using NASA's tracking and data relay satellite system. At T-minus 39 minutes, 16 seconds and counting, this is Falcon Launch Control. This is Falcon Launch Control, T-minus 34 minutes, 25 seconds and counting. While most are familiar with NASA's interest in sending research to the International Space Station, in 2005, Congress designated the U.S. portion of the space station as a national laboratory. And in 2011, NASA selected the Center for the Advancement of Science in Space to manage the national laboratory. Known as CASAS, the CASAS mission is to sponsor commercial and academic research intended to benefit life on Earth. SpaceX CRS-5 will mark the fourth official series of investigations that will have been sent to the space station under their manifest. On this mission, CASAS, along with NASA and the National Institutes of Health, are sending a joint investigation on the similarities between the immune system in microgravity and aging in adults. To learn more about the investigation, we're going to look now at a very short video brought to us by CASAS that discusses this aspect of CASAS and the National Laboratory. 3, 2, 1, 0, and launch of the SpaceX Falcon 9 rocket.
On SpaceX 5, we're launching an experiment from Dr. Millie Hughes-Fulford's lab. And Dr. Hughes-Fulford is going to be looking at the immune system in space and studying how the effects of microgravity on the immune system are similar to the effects that happen in aging adults on Earth.
To dream and to explore is the nature of humankind, and to find new knowledge is key. If you think of it, we all evolved in a gravity field. When we go into space flight and we have microgravity, we have eliminated one variable. In mathematics, if you get rid of a variable, you can solve the equation. And we're able to look at the immune system in a whole new way that has not been possible before.
Dr. Hughes-Fulford is specifically looking at T cells, which are a type of cell that actually orchestrates your whole immune response.
When you have an infection, the T cell turns on molecules that are part of the immune response. What we're looking at are the microRNAs, and the microRNAs are the very earliest molecules responding. And so if you think of the immune system like rain in the mountains going to a stream, going to a river, then ending up in a waterfall down to the ocean, right now you're treating the waterfall. What we want to do is treat the raindrops.
So in microgravity, if we look at the RNAs that are absent from this immune response, we can identify potential therapeutic targets, drug targets, that we can introduce into the cells of aging adults and hopefully promote appropriate and effective immune responses and fight off infection.
I think the International Space Station is an opportunity for the entire scientific world. It's the only place I know that you're not really competing with each other over land or politics. You get together and you work together to make something work.
This project not only involves Dr. Hughes-Fulford's lab here at the VA Medical Center, but it also was sponsored by both the National Institutes of Health and NASA. CASAS can actually facilitate research that brings together multiple parties to really do amazing science and things that are going to really bring back meaningful medical advances to benefit people on Earth.
And this video from CASAS demonstrates that the International Space Station is really hitting its stride in doing the research that the space station was originally intended to do when it was built. So at this point, the astronauts as well as the ground teams are supporting science investigations on a day-to-day basis that benefit people here on Earth. And most of what's on the Dragon capsule today is part of that. We're at T-minus 29 minutes, 50 seconds and counting. This is Falcon Launch Control.
Purge ISO cycle complete.
This is Falcon Launch Control, T-minus 27 minutes, 54 seconds and counting. This is a live shot taken in front of our one of our long-range optical trackers of the International Space Station. That is a live picture of the ISS. It is going overhead of Cape Canaveral right now. And as mentioned previously, at the time of launch, the space station will be located at a location over southeast Iraq at an altitude of about 261 statute miles. About 10 minutes after launch, Dragon reaches its preliminary orbit and then deploys its solar arrays and begins a carefully choreographed series of thruster firings to reach the space station. After the two-day trip, NASA astronauts Barry Wilmore and Terry Virts will use the station's 57-foot robotic arm to reach out and capture the Dragon spacecraft as they operate from the station's cupola. Ground commands will be sent from Houston for the station's arm to install the Dragon on the bottom side of the station's Harmony module for it to stay at the ISS, and then by the next day the crew will be ready to pressurize the vestibule between the station and Dragon and will open the hatch that leads to the forward bulkhead of Dragon. During the next 4 weeks, the crew will unload the spacecraft and reload it with cargo for return to Earth. About 5.5 hours after it departs the space station on departure day, it will splash down in the Pacific Ocean off the coast of Southern California. Over the last 20 minutes or so, the Falcon 9 has been ready for launch, placed in its launch configuration. And coming up at T-minus 20 minutes, the final launch countdown preparations by the SpaceX launch team will begin. At T-minus 24 minutes, 44 seconds and counting, this is Falcon Launch Control.
OSM-LC on countdown net.
OSM.
Verify flight hazard area roadblocks are established.
They are established.
Copy.
This is Falcon Launch Control, T-minus 20 minutes, 20 seconds and counting. The first stage vehicle is fully fueled, and we're standing by to begin final launch preparations, which occur at T-minus 20 minutes and counting. This is Falcon Launch Control.
Setting warning to thermal count.
All stations stand by for T-minus 13 minutes to pull for ready for launch.
All right, CEO and countdown. Team is ready to go. We're going to watch the TVC2 wiggles and thermal count and may call a manual aboard then. So pay attention to that.
Copy.
This is Falcon Launch Control, T-minus 13 minutes, 50 seconds and counting. In 13 minutes, we'll have a readiness poll of our 14 console positions. And then the auto sequence will start at T-minus 10 minutes and 30 seconds. At that point, we'll lead into chilling the 9 first stage Merlin engines. And at 8 minutes, Dragon will go to internal power. Dragon terminal count auto starts at T-minus 5 minutes 30 seconds. And then the Falcon 9 will go to internal power 4 minutes 46 seconds before ignition. And we'll start terminating our liquid oxygen topping at T-minus 3 minutes and 2 seconds.
Prop go.
AVI.
AVI is go.
GNC. Ground.
Ground is go.
VC.
VC go.
GC.
GC's go.
RC.
RC go.
OSM.
OSM go.
ROC.
Rocks go.
CE.
Go.
MD.
Dragon MD's go.
LD verify go to initiate terminal count.
This is LD. Go to initiate terminal count.
Copy proceeding within countdown master.
VCDC start the terminal count auto sequence set to start at T-minus 10 minutes.
Copy.
If a hold is called from this point forward, the terminal count auto sequence will be aborted. Indicate an abort or hold condition by saying hold, hold, hold on the primary countdown net. In this event, the VC will immediately abort the auto sequence. The VC shall not abort the auto sequence after T-minus 10 seconds, and operators shall not call a hold after T-minus 10 seconds. If a hold is called, all operators proceed to the terminal count abort steps in section 10.61.
We're hearing our SpaceX launch conductor, Brian Childers, along with our SpaceX launch director, Ricky Lim. And we have confirmation that the Dragon auto sequence has started. And we'll have confirmation that all of these activities are continuing in work. Still on schedule for a liftoff at 6:20 a.m. this morning.
Attention all personnel, stand by to pick up the count. T-minus 10 minutes and counting on my mark. Three, two, one, mark. VCDC announced auto sequence has started.
Terminal count has started.
Dragon terminal count has started.
GCVC, stand by and fire X.
Standing by.
RC, start the tracking camera video recorders.
Started.
OSM, set launch enable to flight.
Flight.
Pre-valves open, starting M1D chill. Ground T-tip system setting up. Securing Dragon chilled water. KCS closeout.
It's a live shot of our Mission Operations Control Center in Hawthorne, the SpaceX Control Center, which will be controlling after liftoff. Coming up on T-minus 7 minutes.
Stage 1 heaters closing out.
T-minus 7 minutes.
Dragon has been in the process of going to internal power.
Stage 2 heaters closing out. Falcon switching to internal power, and the ground TVC system is setting up.
And we have confirmation Dragon is now on internal power. The Dragon terminal count auto starts at T-minus 5 minutes 30 seconds.
T-minus 6 minutes.
Tanks pressing for strong back retract. Vehicles on internal power. Strong back lower auto sequence started.
Falcon is on internal power. Strong back will begin retracting.
Final stage 1 fuel bleed started.
T-minus 5 minutes.
Starting MVAC TVC motion.
Turning on the telemetry and video transmitters.
T-minus 4 minutes.
Strong back is retracted.
Stage 2 tanks minute.
Strong back is fully retracted.
FTS is on internal power. FTS is armed.
GNC verify nominal stage 2 TVC motion.
Closing out of helium fill.
LD verify go for launch.
Stand by on that call, LC.
Stage 1 tanks at flight pressure. Final M1D chill.
Rock verify range go.
Range green.
Hold, hold, hold.
Terminal count abort.
All stations proceed to 10.61, terminal count abort.
Launch director on countdown 1. Hold, hold, hold. Stop the clock, LC.
Clock stopped. CE set warnings phase to terminal count abort. VC verify terminal count abort has started and terminal count is no longer running.
Verified, terminal count abort's running.
VC DC verify we are not in startup.
Verified.
Not in startup.
GCVC reactivate fire X if fire is present.
Copy.
Secured.
OSM verify ready to safe FTS and report.
OSM ready to safe FTS.
OSM set verify launch enabled to inhibit.
Inhibit.
GC prop AVI and LC, are you ready for strong back raise? Verify the cradle arms are fully open and clear of the rocket.
Props ready. GC's ready.
LC's ready.
AVI ready for strong back raise?
AVI is ready.
Copy.
DC verify Dragon has aborted it and is in a stable configuration.
Dragon has aborted and is in manual.
Strong back raise started.
GC verify fill manifolds are vented. Stage 1, Stage 2 locks and RP interfaces.
Verified.
GC verify all water systems are safe.
Saved.
GC verify TVC tank vented.
Vented.
GC verify TTEB system is safe.
Saved.
GC verify LOX load is in a stable configuration.
LOX load is stable.
And the countdown has aborted for this morning.
As far as the disarmed FTS on external power, FTS state is saved.
Copy.
Have an issue that developed fairly late in the terminal count.
CC
EM countdown, I'm going to brief the anomaly on the anomaly net.
And what appears to have happened is some actuator drift fairly late in the count on the thrust vector control system that would have triggered automatic abort in the final portion of the countdown. Don't have all the information on the problem other than there was some actuator drift that was gradually becoming a problem that would have actually terminated the terminal count automatically.
Cradle close started.
So that actuator drift issue will have to be resolved before Friday's launch attempt. And our launch time on Friday for Friday's launch attempt is 5:09 a.m. But once again, the launch countdown has been terminated for today due to a Falcon 9 launch vehicle issue that will be resolved over the next couple of days before a launch attempt on Friday at 5:09.
Cradle close complete.
LC Rock, count on it.
LC.
Just want to pass, range is red.
Copy.
And the strongback has returned to position.
GC, prop, and LC, are you ready to vent the tanks?
Prop's ready.
JC's ready. LC's ready.
Copy. Tanks vented. Falcon switching back to external power.
Vehicles on external power.
AVI instruct VC to cycle power on transmitters to keep the temperatures within launch limits.
Copy and work.
Attention on the countdown net, the vehicle is now safed. Please stand by for a briefing by LD on the abort.
LD on countdown 1, LC. The team is looking into the second stage TVC actuator, but go ahead and scrub for today, given the instantaneous window. So please proceed with scrubbing, offloading propellants.
Copy. Attention on countdown net. This ends our operations on countdown net. We'll move all operations back to launch vehicle net. OSM, reestablish roadblocks at the BDA for launch scrub.
We'll put it in work.
This is Falcon Launch Control. Once again, we did scrub for today. The scrub occurred at T-minus 1 minute 28 seconds, and it was due to second stage issues related to the actuators on the second stage, an actuator drift, which was detected late in the count. Once again, our launch attempt on Friday planned to occur at 5:09 a.m. on Friday. Our launch coverage on NASA television would start at 4 a.m. And if this abort had not been called by the launch team, it would have triggered an abort. But the understanding at this early point is that the thrust vector control system actuators had a drift which would not have permitted an acceptable liftoff today as far as the second stage. First stage appears to have performed nominally and was ready for launch. So right now the team is preparing to detank the rocket. I think the launch team is still looking at the vehicle data, get a better resolution of the issue. And the team is taking the opportunity to look at some other minor issues that came up in the terminal countdown phase. And I have received word that there will not be a post-scrub news conference, news briefing. But for further information on the circumstances surrounding the scrub and our status of our next launch attempt currently planned for Friday, you can go to www.nasa.gov/SpaceX. So at this time, this will conclude our launch countdown coverage for the SpaceX CRS-5 mission. This is Falcon Launch Control.